Welcome to Math331 problem solving lecture 32, 33, 33. This was probably the worst performance I have seen since the last time I taught this class on a final at Williams. And as I was remarking to some people before class started, this is the only final at Williams where I do not feel comfortable in math that I could pass. All right, so I have not really looked at the problems other than essentially A1. What I want to do now is talk a little bit about these problems. And so I thought we would do A1 first, and then after that, if there are any problems that people found interesting, or even better, interesting where they had an idea on how to solve them, we would move to that next. So A1 is a great Putnam problem. We want ordered pairs A, B, positive integers, such that 1 over A plus 1 over B equals 3 over 2018. And it basically satisfies the requirement of somewhere in the exam the year occurs. And I guess it also occurs in problem B6. What were you supposed to do to the number 2018 before the exam? Get its prime factorization, right? You had been told numerous times, factor 2018, and know what its prime factors are. So how do you factor 2018? Is 1009 prime?
Yeah.
How high do you have to check?
Square root of 1009.
Square root of 1009. So how big is square root of 1000?
Like 31.
Yeah, so it's not horrible. Right? Because we know if we can write a number as x times y, if both x and y are less than the square root of your numbers, so it's the product. So you only have to go a little bit more than 30, because 30 squared is 900. So if you don't remember that 1009 is prime, it's not horrible. Okay? We will accept that 1009 is prime. I admit I did not check because I wasn't taking the exam. So my first question is they want to know all the pairs of positive integers such that this is true. What are your thoughts when you see that?
Well,
yes.
First I thought, well, I have found one, right?
Yeah. So can you find one?
Yeah. So
what's the one you find?
We have 1 over 2018 plus 1 over 1009, and then the contrary.
Right. So that will, and there you can see the 3 coming into play. And this will give 2 solutions. So we now have 1009 and 2018, and 2018 and 1009. Okay, so we know at least there's one solution. What's the next question you might ask?
Well, the next thing I did is I developed 1 over A plus 1 over B,
right,
and set it equal to the development of 1 over 2009 and 1 over 2018.
Okay, but before we do that, I'm just like a higher level. What question might you be asking? Do you think there's a finite or infinitely many solutions? So just get some intuition. Do you think you should be able to do this finitely often or infinitely often? It feels finite. As A and B get very large, what do you think is going to happen?
Well, at some point we won't be able to go back to 2018.
I'm sorry?
We won't be able to go back to 3 over 2018.
Yeah. I mean, if A and B is sufficiently large, there's no way that's sum. So if both A and B are large, it can't happen. If both A and B are small, there's only finitely many things to check. So there's only one case left, where one of them is small and one of them is large. But if one of them is small, then the other one is uniquely determined. So we could actually get some intuition, break into cases. This will not help us solve it, but it would reduce it to a finite calculation where if you had plenty of time, you could then just go through all the possibilities for A and B. The idea is it's probably going to be too vast to do by brute force on the exam, but maybe not. So can you give me a size for A and B where if A and B are greater than this, there's going to be no solutions?
Well, greater than 2008.
So no solution if A and B are greater than or equal to 2018. Okay? Because if we do that, then we'll get 2 over 2018. Can you do a little bit better than 2018? Can you give me a smaller number where if A and B are both greater than that small number, there's no chance?
But if they're both greater than 1009.
So if they're both greater than 1,000, well, if they're both 1009 plus 1009 would be 4 over 2018. So that's a possible. So it's possible that there could be solutions if A and B are both greater than 1009.
Yeah, but because 1009 has no factor.
Well, I'm just saying just really crude arguments. So that's becoming clever, but just a really crude argument. How can I improve the 2018?
2/3.
Yeah, 2/3 of that. Right? Because 1 over A and 1 over B, if I want them to be greater than or equal to a fixed number, then the best I could do is if whatever that fixed number is both of them. So if that number is n, I would get 2 over n equals 3 over 2018, which would imply n would be 2018 times 2/3. All right, so approximately what?
1346.
So we can already say that once A and B are greater than 1346, there's no solutions. Now we're down to, without even using any clever math, slightly over 1,000 possibilities to check. Because we only really need to check A and B. So now, if A and B are small, can there be solutions?
Not if they're less than 673.
Yes, if both A and B are too small, there's no solutions. So, no solution if A, B are both less than or equal to 673.
Well, 672. If
Okay.
it's less than
Okay. Something like that. So we're getting some ranges already. Now, if one of the A's is small, without loss of generality, we could assume maybe A is less than or equal to B. And then for each choice of A, there's going to be at most one choice of B. What I want to do is I want to be able to use this to say that there's only finitely many solutions. So, without loss of generality, A is less than or equal to B. Given A, if there exists a B, then we would have 1 over B is 3 over 2018 minus 1 over A. So B is uniquely determined. Yes?
Sorry, for case 2,
Yep.
actually it's only one of A or B has to be less than or equal to 672.
Okay.
So for both, you could get a...
Okay. If A or B. Because once one of them is very small, then this whole sum is going to be larger then. So we already know if we're looking at the smallest one, if A is less than or equal to 672, we don't have to worry about it. And then the question you might want to say is, if A is the smallest one, how large could it be? And still have a hope of a solution. So this might even be a better way of going about it. So again, to me, it's the thought process that matters. If A is always less than or equal to B, no solution if A is less than or equal to 672. And then if A is the larger one, if A is the smaller one, how large can A be and still have a chance of a solution? Well, if A is 3 over 2018, we could just barely have a solution, right? But the best we could do in terms of making this large is if B is the same as A. So I want to say that this is roughly where we would get our 2/3 coming in now. Is that if A gets too large, there's no chance of a solution. It can't add up. If A is less than or equal to B, no solution if A is greater than or equal to, what was it, 13?
Just twice that. Right, 13.
40.
And this is basically coming from the 2/3 times the 18. Because A is the smaller one, the largest this could be is if B equals A. So if this is the case, we actually have a decent range of A. It's only a range of 672 numbers. You've got 3 hours. No, I'm being serious. So 3 times 60, it's 180. You got 180 minutes, right? Let's throw off 40 because you looked at a couple of other things. So you have 140 minutes. You have less than 700 things to do. Is this doable?
I don't think it is. I think we'll fall just short.
I feel like if you had enough intuition for some answers that you knew just like wouldn't work
Well,
immediately, then
you would immediately get 1 over b equals 3 over 2018 minus 1 over a. So this would then become 3a minus 1 over 2018. So b would equal 3a minus 1 over 2018. So now you just start running through a's and seeing when is this a multiple of 2018. Well, every time you increase a by 1, you increase the numerator by 3. So if you just look at this modulo 2018, I don't know. I think we could brute force this in 140 minutes. For class on Wednesday. Because what we could do is we could actually split it. We could split people into 2 groups, right? If we have 7 people, everybody gets a range of 100.
Can we just run it on a computer?
Yeah.
Well,
we're not in the Putnam now.
Why are you saying no to this? We know the answers.
We know the answers.
Yeah.
What I'm just trying to get at is this a Putnam problem that could have been brute forced without knowing too much stuff? I think so. I mean, I think looking at this point by just doing some quick checks and seeing what are the possible ranges for A and B. Without loss of generality, assume A is the small of the 2, and then if A and B are not the same, then you have to remember to count the pair twice. We're down to checking less than 700 things. If we look at it like this, every time we increase A, it's going to be very fast to check, right? So I think it's actually brute forceable because these will be very fast to check. You'll be able to jump a lot. All right, let's now try to do it with more mathematics and more cleverness. All right? But it's nice to show that it's a finite calculation. So did people cross multiply and multiply by A times B?
Yeah.
And so when you do that, you'll get A plus B times 2018 equals 3AB. Or 2 times 1009 times A plus B is 3AB. So what can you immediately conclude from this?
A plus B has to have some multiple of 3.
Yeah. So either A and B are both multiples of 3, or if one of them is 1 mod 3, the other one is 2 mod 3. So we know 3 has to divide A plus B. So that's a huge help. We also know 1009 has to divide either A or B. Well, to me, that's the more important one, right? So what I would say is, we'll assume 1009 divides A. So what would we write is 1009 times M.
Well, but consider 1009 or 1, right?
I'm sorry?
It's either 1009 or 1.
What do you mean by 01?
But like the only divisor of 1009 or 1009 and 1.
Well, but I'm saying we know 1009 divides the left-hand side. So 1009 has to divide either 3 or A or B. And without loss of generality, we're not assuming now that A is the smaller of the 2. If we were assuming A was the smaller of the 2, we couldn't necessarily assume 1009 divides it. But since we're just assuming that A and B are just general numbers, then we know 1009 divides one of them. Okay. So what do we know about 1009 mod 3? It's 1. So 1009 is 1 mod 3. So this is also congruent to m mod 3. Just in case that matters, we knew that there was some information about a and b and their sum being a multiple of 3. So if m is a multiple of 3, then so is b. All right. Next steps, what should we try now? So one thing is we could try just various choices of m. We could try m equals 1, m equals 2, m equals 3. So if m equals 1, we get 1 over 1009 plus 1 over b equals 3 over 2018. Is there a solution? Yes. b equals 2018. We could try m equals 2, and we would get 1 over 2018 plus 1 over b equals 3 over 2018. So we would get b equals 1009.
But we already knew this
Right.
because it's uniquely determined, right?
Right, this is basically just, it's our same solution, just reordered. But, we know a has to be of this form. So we've already tried m equals 1, m equals 2. We could now try other values of m. And see, do other values of m lead to a solution? And you could just try a couple of values of m and just try to build up some intuition. Or we can try to do some more analysis up top. So again, if I can ever reduce a problem to a finite calculation, this is really good. What if m gets extremely large? If m gets extremely large, do we now know that there's no chance of a solution for 1 over b?
We said we had a bound on A and B, so.
Well, but beforehand we had assumed that a was the small of the two.
Oh, right.
So we don't have that. But imagine a is extremely large. Then 1 over b has to be approximately 3 over 2018. And I think if we make a sufficiently large, we can say there's going to be no nice reciprocal of an integer that is going to be extremely close to 3 over 2018. So I think you could show that if you got an m sufficiently large, there would be no solution. But you would have to prove something like that. So, the question is, when we have 3 over 2018, what are the closest reciprocals of integers to it? So what's nice is we can actually plot this a little bit. And again, I'm trying to do this problem using as little math as possible, reducing things to calculations. What's 3 over 2018? Just to be safe, I am going to divide that on my computer. Okay. So 3 over 2018 is approximately 1 over 672 with 6 repeating. So here is 3 over 2018. Here's 1 over 672. Here's 1 over 673. And those are going to be the closest 1 overs to us. If 1 over a is truly, truly large, if a is truly, truly large, it's not going to be enough to move us this distance. Because, for instance, let's say 1 over b was over here, or 1 over b was over here. The most we can move it is 1 over a. And if 1 over a is truly tiny, if 1 over a is less than these two,
Oh, that's fine.
right? So I look at the distance 3 over 2018 has to the two nearest. Yes?
Although you really just need to look at the distance to the 673.
Right, because the 673 is going to be the closer.
And 672 is not possible, because you'd have to go in a negative direction.
Yeah, barely proved.
Okay, good. So that's even better. So noting that, we only have to look at this. We have 3 over 2018 minus 1 over 673. I'm sorry?
That does happen to be the solution.
And it happens to give a solution?
Millions something.
Oh, nice. So
I ran that completely by accident.
So 3 times 673 is 2019 minus 2018 over 2018 times 673. So we get 1 over 673 times 2018. And that's nice. So that is the distance from 3 over 2018 to the nearest 1 over an integer. And so when we look at, if we have 1 over b is 673, then we could do it. So if 1 over b is 1 over 673, then 1 over a is 1 over 673 times 2018, and that is a multiple of 1009. So this gives us 2 more solutions. Are there any other solutions? Are there 6 solutions total? Yes.
I found another pair. I missed this one.
Okay.
Yeah, I don't know about the pairs.
The other pair is 674.
Is 1 over 674?
Yeah. Because like you get one of them is like 2 times 337, I think.
Okay.
And then the other is 1009 times 337. And that just ends up.
What this is saying is, if a is sufficiently large, then 1 over a is not going to be enough to move us from 1 over an integer. So this is no solutions beyond a equals 673 times 2018. This doesn't mean that these are the only solutions. But what we're talking about is, if you have the reciprocal of an integer, and I want to move to 3 over 2018, I'm moving by 1 over a. And if 1 over a is too small, it's not going to be enough to move me here. So this tells me that once a is 673 times 2018, that's the last time I could move enough. There could be an a that's small that works. So now we only have 673 multiples of a to check. Right? Yeah, we were trying to figure out what possible values of m work. This tells us that there's at most 673 things to check. We know m equals 1 works, m equals 2 gives the corresponding thing, m equals 673 works. And then the question is, are there any other m's that work? So we have now again reduced it to a finite calculation. This one doesn't seem as pleasant as the previous. We now have to look at all the values of m. Well, we could try and just see what the solution would look like. So if we have 1 over 1009m plus 1 over b equals 3 over 2018, and this is the same as 1 over b is 3 over 2018 minus 1 over 1009 times m. So I need to multiply this by 2 and this by m. So I get I get 3m minus 2 over 2018m. Does that look right? So we then get b would equal 2018m divided by 3m minus 2. So is that similar to what you got?
Yeah.
Okay, so now we just have to check and see for what values of m will this be an integer. we know we only have to check up to m equals 673. But of course, to some extent, well, the numerator is always going to be larger than the denominator. They're both, it's going to look like 2018 m over 3m. All right, so now, is this similar to what you were doing?
Yeah, and then I just noticed that 1009, because we noticed earlier that 1009 is 1 mod 3, right?
Yes.
If you do minus 2, so like you know that there has to be like a clean figure.
Right.
And 1009, I just noticed that if you have 1011, since it's 3 ones, it's divisible by 3.
Okay.
And so I use that to get 337.
Okay.
Yeah.
So now let's see. We'll kill. All right. So we'll come over here. So we have. Did somebody see something better? Or?
No.
And you said pi m equals.
337.
Okay. And so when you do that, 337 times 3, so you get 1009. Okay. And that will yield b equals 2018 m over 1009. And so you then get b equals 2m. Oh, wait, m is 337. Okay. So it would become 4, 7, 6. And that was the other solution.
Yes.
Okay. So we now found 2 more solutions because we can put them in either order. Is there any other solution to 2018 m over 3m minus 2?
Well, it looks like it.
So
It looks like as we're going to increase m, we're going to have to multiply it later.
So one of the things we note is any multiple of m does not divide the denominator unless it's 2. So 3m minus 2, its only possible prime factors can be 2 or 1009.
Right.
So I think that's the key observation now.
Yeah.
So prime factors of 3m minus 2 must be 2 or 1009.
Or, can you say instead that the value 3m minus 2 has to be a factor of 2018? So is that the equivalent?
Yes. That might be a little stronger.
Yeah, because like I think that's how I phrased it, but I don't know.
Sure, that's a little bit stronger because we know this has to divide.
Yeah.
But you also have the m up here, so it doesn't.
You
But
can kind of
we know
ignore
can't.
that, right? Because like you just need b to be an integer, right?
Right. The only thing I'm worried about is if m is 2 and you have 2 here, you could actually have a factor of 4 maybe, but
But then
no, but then this will be.
Well, didn't we already do m equals 2? So is that
Right, I was just worried about what if m is even.
For example, if like m equals 4.
So if m equals 4, you get 12 minus 2, which is 10. But you've got a factor of 2 here. The danger is could you have a multiple of 4 down below, which now comes up there. That's why I was just trying to be a little bit more careful.
Yeah.
Well, you have, right? Because now you have like 2 times 1009 times 4. And then like if you check modulo something, you'll find that there is one.
Okay, so when we took 337, we got 1009. So we weren't getting any factors of 2 or 4 here. I'm just slightly worried because 2 could divide m, and 2 will divide 2. So if m is even, then there is the danger.
Well, in the case that m is even, you can factor out the 2's from.
Yeah.
Did you two have a question or comment?
We had comments, but I
No.
Negative.
Yeah, we didn't get this far with the problem.
Okay.
I got something, but I don't think it was what
Okay.
it is.
So if you know that m is even, then you can rephrase it as 2k, right?
Right. So
Yeah.
one thing is
So
to
you can factor
explicitly
it out.
write that in,
And write that as a
and then
factor.
pull out the 2.
Yeah.
So there is the right. I'm wondering is do we have to go through that, or can we somehow
Yeah.
avoid that? This is the only issue. Is we know that the prime factors of 3m minus 2 must be 2 or 1009. And so I'm wondering if that's enough to help, rather than saying it has to go into 2018. So we've already done m equals 1 or 2.
Well, we could check if they are equal for modulo m, right? And then.
Well, mod m, we know that 3m minus. If m has any prime factors other than 2, it's not going to have anything in common upstairs and downstairs. There'll be something different downstairs than upstairs, I believe. So the question is, what's the fastest way to show that nothing else works? So you got m equals 337. So we need 3m minus 2 to either be 2, or just powers of 2. If m is powers of 2. Or we need to show that it's got to be a multiple of 1009. So looking for multiples of 1009 is nice. So one thing is maybe say, first let's look and see when could 3m minus 2 be a multiple of 1009. And then you'll get m equals 337, and then the next one we already know, and then that's it. So then I think the only thing that would be left is 3m minus 2 has to be a perfect power of 2. So the problem doesn't seem that bad at first, but to just go through and eliminate everything without doing brute force calculation, it's starting to become involved. We have ranges, and this is screaming at you to write a computer program. And if you write the computer program, then you'll very quickly find the answer. But can you just do this on pure theoretical grounds? So now over here, if 3m minus 2 is a multiple of 1009, that's not so bad. So do 3m minus 2 a multiple of 1009 first. So we can do that without any trouble. And we just solve when does 3m minus 2 equal 1009, when does it equal twice 1009, when does it equal 3 times. By the time we get to 3 times that, we're beyond the range from what we did before. This idea that we have to be very close to 3 over 2018, we can't move too much, allows us to very quickly eliminate this. So the only thing that's left is if 3m minus 2 is not a multiple of 1009, but it's perfectly to go into 2 times m. Well, this probably won't be too bad. How many powers of 2 could we have in 3m minus 2? If m is 3, if m is 4, we would get 12 minus 2, which is just 1 power of 2. If m is 4, we would get, if m is, so let's do now m equals 2k.
Well, if m is 6, for example, we have 16,
Yes.
right?
Right, so if m is, and then that would be a possibility.
So it looks like it's like 2, 6, 10. We
Right.
are just jumping one
Right.
and doing 12
Right.
or 2, right?
Yes.
But so I'm a little bit confused. So we're assuming that it doesn't go into 1009 now.
Right, because we've handled those cases.
So you're saying 3m minus 2 has to go into 2m,
Has to go into 2m.
but 3m minus 2 is greater than 2m.
Ah, good. It'll be greater than 2m very quickly.
Right. So
Okay, great. That's much better than looking at powers of 2. That's much better, right? So we now need 3m minus 2 divides 2m. Since this is going at the rate of 3 times m and this is going at the rate of 2 times m, 3m minus 2 less than equal to 2m, this is the same as m is less than equal to 2. And we've already checked those cases. So that finishes the proof. And then we don't have to worry about these annoying powers of 2. Right? No, but there has to be a nice way to go through the algebra in something like this. They're not going to have it too painful. But there were more things. I did not prepare this problem at home, as you can probably tell, deliberately. There was more subtlety to this than I thought. And the question is, just stepping back, what is the best way to approach a problem like this? First, you have to know the prime factorization of 2018. If you do not know the prime factorization of 2018, you are up the creek. And if you did not calculate that before the Putnam, shame on you. Okay, I'm the professor. I'm allowed to give myself a pass because I was not taking the test. But you need to know that.
I did not calculate it, but when I saw 1009, I was like, it's prime. Otherwise, I'm screwed, so it has to be prime.
Do you know the joke that all odd numbers greater than 1 are prime? So the mathematician is 3 is prime, 5 is prime, 7 is prime, the rest follow by induction. The physicist is 3 is prime, 5 is prime, 7 is prime, 9 experimental error. Astrophysicist, I think, is order of magnitude. Engineer is 3 is prime, 5 is prime, 7 is prime, 9 is prime, 11 is prime. And then my favorite, though, is the computer scientist. Does anybody know the computer scientist? 3 is prime, 5 is prime, 7 is prime, 7 is prime, 7 is prime, 7 is prime. But yeah, I mean, it's quite likely that 1009 is prime. Alright, so for this, let's step back. The very first thing I did when I looked at this is like, alright, I'm not going to get most of the Putnam problem. I'm going to spend a lot of time on A1. Can I somehow get a bound on where I need to look? And is it so bad that without being clever, I can't do it? Or maybe if I'm just a little bit clever, I can brute force it. And we saw that, well, once you fix A, then B is determined. And we saw that once they get too large, there's not going to be any solutions. If they're too small, there's not going to be any solutions. So there's a sweet spot. And you just have to check in that range. It was a little bit long, but we could do it. Then we started looking at, well, let's cross multiply. And rather than having reciprocals, let's have everything now involving just integers. And so when we did it like that, we very quickly got into this nice equation. We never really used m mod 3. We never really used 3 divides a plus b. There didn't seem to be a need to do that. And we knew that 1009 had to divide either a or b, so let's just write a as 1009 times m. And then we could quickly look at some small values of m. And the question was, can we at least make it a finite calculation by saying that from some point onward, we don't need to look? And so if we didn't do that, when we came to the second part over here, when we now are able to rewrite it, so we now have b equals the following, if m could be arbitrarily large, we would have to keep checking all multiples. But we know that we can't move too much. As a gets very, very large, 1 over a becomes very, very small. So 1 over b has to be almost at 3 over 2018. And it's sadly been erased, but we know the closest you can be to 3 over 2018 is a fixed amount. And so once a is too large, you can't move enough to get there. And so that allowed us to now bound m. So now we only have a small range of m. It's like, I think, 670 something to check. But when we looked at this, we could say, okay, well, we know this has to divide the numerator. If m is very, very small, and if m equals 1, then you get just 1. If m is 2, you get 4, which works over here. Those were the cases we've already done. And then as m starts to get larger, if this has a prime factor different from up top, you're in trouble. So its prime factors has to be basically just 2, or just 1009, or maybe both of them. And the good remark was, well, once m is greater than 2, 3m minus 2, 3m minus 2 will not be able to divide 2m, but it could possibly show an extra factor of 2.
Yeah,
and that's just,
we trade 6 in first.
Yep, right? Yep. And so if we take m equals 6, we would get 18 minus 2 is 16. But if we take m equals 6 up top, we don't have enough powers of 2. So m equals 6 does give us a perfect power of 2 downstairs, but we don't have enough powers of 2 upstairs. So we can eliminate 6. But it's something we have to be concerned with. So we can say, when could you be a multiple of 1009? Fortunately, there's only 1 or 2 possibilities. And now we're just left with the new one which we found. Okay. So I thought this was a fun problem.
It's solved.
I would say this is solved at this point.
So this is the sixth verse that we have.
So there are 6 solutions. And I will check the solutions from God. Yes, well, these are 2 of my friends. Yep, there are 6 possible pairs.
Wait, they already told me the
Oh, yeah.
In 10 minutes.
Oh, I was wondering, like, because I think who was it? Goldmacher, right?
Yep.
Was he doing the exam while we were taking it?
I don't know.
Oh.
The people I'm referring to are, I think, 2 4-time Putnam fellows who have a web page where they just post the problems and solutions.
Wow.
And so my favorite is I'll wait till there's a recording malfunction, and then we'll have a recording malfunction now.
How long do you think it takes for them to finish?